Howdy, everybody. My name is Ian Wilhite. I'm the project lead for the Turtle Project, the Disaster Response Observation Network, or DRON. So starting off a little bit about the problem definition, what we're actually trying to do. So DRON is a research undergraduate proof of concept that aims to use UAVs for structural fires. First responders, the hardest thing that they do is trying to figure out how many people are inside the building, where it's safe to enter, and what paths they can take through the building to get where they need to go. And so what we're doing is we are developing autonomous UAVs with integrated sensors and a feedback system, a user interface that is clearly and plainly presenting the thermal and physical data about some structure, so that we can help first responders better identify those entry points and identify potentially people inside. So a little bit about some of my relevant motivation. So summer of 2024, I worked as a trail crew foreman in the conservation department at Philmont Scout Ranch. And back in 2018, there was a Ute Park fire that took about a third of the property of this massive ranch out in northern New Mexico. And in that summer, the entire conservation department, the people that went on to become my coworkers, were all almost immediately turned into this impromptu fire response group for what was one of the largest fires in northern New Mexico in the last decade. And so this is something that matters to me. I think it's really important that we can be utilizing technology to better our ability to respond to these types of emergencies. And so, of course, wildfires are pretty big and hard to emulate. So let's start a little smaller. Let's start with a house fire. So what we're doing, UAVs are known for their ability to get somewhere fast. They are fast, they are cheap, and it's pretty well researched to be able to put RGB thermal and LiDAR sensors on board. And there's a lot of existing literature that goes out. You have simultaneous localization and mapping problems. This is where you're A, trying to figure out where you are, and then B, where your environment is, and then trying to do both of those things at the same time, and using your surroundings as a way to localize yourself. This is a lot of the packages that are used to help drones navigate and map from around their surroundings. The other half of this literature review is UAVs, because of their cost effectiveness, because of their small scale, are very often implemented in swarms. And so being able to use your collaborative map to be able to better localize each of your individual agents. This is like collaborative simultaneous localization and mapping, as well as your environment moves, fires change. And so being able to account for that in your universal world map that you are generating as your scene progresses and your UAVs are collecting new data. So a little bit about, okay, this is the goal, this is the system, this is the theory. What did we do? What have we done? So mechanically, we of course have our chassis. When you're putting a bunch of custom sensors on an airframe, there's not a lot that you can just buy off the shelf that works for that. You have to make it from the ground up. On the left is the old chassis from last spring. On the right is our chassis from this fall. And on the middle is the picture taken of a handful of our previous iterations of chassis from our field test earlier this semester. Most notably, when you're flying around, there are obstacles, there's rain, there is a lot of sensitive components that need to be protected from the elements and from the outside world. And the chassis, a lot of other alternatives would be open to the air. And if we intend on going into contested environments, then this is something that's really important that we have right. Next is the material selection. We have seen a series of hardware failures this semester because we chose poor materials. And so in material science, there's modulus of elasticity that is relevant to the stiffness. And then there's also the ultimate strength in which it yields. You can imagine that you have a leather belt that's really, really strong, but it doesn't deflect very much. But maybe if you had a rubber belt, it would stretch a lot more and be a lot stronger. And so this one of the big changes that we've made this last semester is switching to a PA, a polyacetic based plastic that has glass fiber built into it, which does dramatically reduce our ultimate strength at the benefit of being able to provide a much higher modulus elasticity, a much stiffer material that is able to, and in being more brittle. This brittle material that is still 3D printable is better able to resist these high frequencies of you have propellers spinning on a motor, you have some very high frequency vibrations, and being able to have a stiffer structure leads to a stronger system that is less likely to fail to vibrational stress. Then our electrical systems. A lot of this is based off of commercial off-the-shelf available components. So we have our flight controller and our electronic speed controllers and motors. Those all came as a package unit. We are retrofitting independent GPS and compass. The IMU comes on board with most flight controllers in the modern era. The somewhat interesting part is the payload. That is on the right side, the Raspberry Pi, the 2 RGB cameras, and a thermal. All of the payload was custom from the ground up. This is a custom operating system on the Raspberry Pi, and a little bit about those sensors in particular. The goal is to be able to map a structure in 3D in real time, and so you need depth, and you can't get depth from a monocular camera. So the binocular stereo vision system allows you to get that depth, and then the thermal camera is of course going to have your thermal data, but just because of cost constraints is going to have a much lower resolution, and so it's very relevant to have multiple RGB images in addition to your thermal ones. I'm going to skip over a lot of the telemetry here. I don't think it's totally relevant to the application. Notably, as we are going to actually implement a lot of this, it's important to have your verification and then your validation. So on a bench test, we were able to get thrust that demonstrated that we would be able to fly. This is just really important before you ever take off, that you are confident that your system is going to be able to perform. Notably, our thrust to weight ratio is about pi, which is just a fun coincidence. And then, of course, there's a lot of online tools for being able to estimate battery life and current draw, but most notably, electronic systems constantly have various failure points, and it's really important that you're building everything so that your battery is spec'd for your load, and that your load is going to be able to enable some reasonable flight time. And then software systems. This is primarily where the novel application comes from here. So first of all, on the top right, you can actually see where we were posting last spring, and that is the 2 stereo images. If you look closely, you can see where people's heads are a little further to the left and right. And then on the bottom there, you can see taking those images, you can plot it, or sorry, the bottom image is not the same as the top ones, but you can take this depth from stereo and you can plot it into 3 dimensions, and then you can paint your thermal data onto it. And so building each of the individual serial drivers, libraries, processing nodes, and being able to put as much computing on our offboard systems so that we can keep our ground control station running quickly and efficiently. That's referred to as edge computing, which is its own field of study. Notably, in our ROS Unity integration, we have all of this data coming in, and we need some way to visualize it. So Unity, the game engine, is what we're using to be able to visualize a lot of this data as it's coming out live. And so the ROS Sharp plugin was able to subscribe to a lot of the topics that we've had. We start by taking it in, and then iterative closest point, ICP, is again another field of research, being able to take multiple point clouds from different points and being able to clean them up a little more neatly. And then of course, as your system changes, you need to be able to take the newer temperature data and discard the old ones while retaining the physical properties of your system. Presumably the building isn't moving, but the temperature is. And then moving away from visualization and into autonomy, this is of course an autonomous UAV. And so the PX4 autopilot was the stack that we utilized. Notably, it has a lot of the hard stuff built in for us. So the localization, being able to serial reading of GPS, and low-level control loops and up to position control is all done commercial off the shelf. What we needed to be able to derive was the waypoints that we intended to proceed to, and the finite state machine that models the motion of multiple UAVs around some point of interest. And then, of course, testing and implementation. It's all on paper, but what about when it's actually in the field? doing the planning for this was very interesting. Finding places where we could both fly a drone and have a very hot source that we could get data sets from. There's a park over in Bryan, Texas. And here is a figure of our low altitude data rich manual collection. Notably, that drone is not flying, and that there is a both textured and thermally rich subject that is being utilized to collect the data set. And then somewhat finally, this is...
Sorry to interrupt, Ian. Is this the end of the presentation? I think the time is up.
Yes, this is.
Okay, thank you so much, Ian.